So today we are going to be talking about basic electrical quantities. And I'm going to kick things off with a brief discussion of the concept of voltage. So I'm going to start with a mathematical definition that uses a little bit of electromagnetic field theory. I understand wholeheartedly that the overwhelming majority of you guys have not had Physics 202 yet. And so I will start off by essentially speaking a little Greek at you, but I'll try to tie it back to things that you have experience with. I'm just trying to give you a picture and an understanding of what voltage is and how to contextualize it in a circuit, okay? So our mathematical definition for voltage that we are literally never going to use in this class is as follows. So I'm going to say that I have some voltage symbolized by the letter V, and this is going to be a voltage which I'm going to call VAB, like so. So this is just the difference in voltage between points A and point B in some network. And this is going to be defined as the line integral from point B to point A. And what we're going to be integrating is an electric field vector dotted in to some differential line element along our path from B to A, whatever that path might look like. Now, I feel like I may be misremembering that you guys have had enough calculus to have an understanding of what a line vector is. You may have had enough a line integral is. I think you hopefully understand what a dot product is, but we're not going to get too buried in the weeds here by any stretch of the imagination. But anyway, so this is the voltage definition for voltage that you would see in most engineering electromagnetic textbooks. And it is a good jumping off point, even if we don't really understand what this particular relationship means, because I'm going to do a couple of very simple manipulations to kind of bring it back around to stuff that we're familiar with, okay? So in order for me to manipulate this guy, though, I do have to introduce one more electromagnetic field theory based relationship, and that is for what's called an electrostatic force, okay? So our electrostatic force, Fe, is nothing more than some charge Q multiplied by some electric field vector E. So this is the force that we feel when, two particles having the same charge repel each other, or two particles having opposite charges attract each other. So this is something that we can physically feel when we are holding static electricity and stuff like that, okay? That's why your hair stands up on end when you're experiencing static electricity, because it all has a bunch of negative charge on it, and it's trying to spread itself apart as far as it can so that those negative charges don't interact with each other because they are repulsive, okay? So what I'm going to do is I'm going to rearrange this guy very slightly, and I'm going to say that my electric field vector E could be written as simply my electrostatic force F sub E divided by charge. And now I'm going to substitute that into my voltage relationship. So that's going to look something like this. So now I'm going to have the integral from B to A of my force divided by charge dotted into my differential line element. And because charge Q is a constant. That's just the value of the charge of a single electron or a single proton. I can actually pull that outside of the integral, and that leaves me with the relationship 1 over Q times the integral from B to A of my electrostatic force Fe dotted into some differential line element dl. Now, how many of you guys know what the integral of force times distance is commonly called?
Work.
Work. Exactly right. So what this relationship represents is that voltage is literally just the work done moving charge from point B to point A in our system, and then we divide that work by Q, the charge of a single electron, okay? So from this mathematical representation, we can actually see a couple of things. So I'm going to give us a word-based definition for voltage here. Let me do it in red. So we're going to say that voltage is the work per unit charge needed to move 1 coulomb of charge from point A to, point B in a circuit, okay? So this definition tells us two things, okay? So the first and most obvious thing is that in order for us to have moving charge in our circuit, we have to have a voltage somewhere, okay? So charge can't move without a voltage present in our system, okay? So think about voltage as the thing that's providing the push to get electrons moving, and we quantify it by this mathematical relationship, okay? Another thing that this relationship tells us is actually what the units of voltage are going to be, because if voltage is the work per unit charge, well, work is typically measured in joules, and charge is typically measured in coulombs. So that must mean that voltage is measured in joules per coulomb. So we're going to come over here to the right-hand side, and I'm going to say that 1 volt, symbol V, is equal to 1 joule of energy divided by 1 coulomb of charge. So those are the units of work, the units of voltage that we're going to use in this class because they are the fundamental units of voltage, okay? Now, there is another definition for voltage that we can glean from this mathematical relationship, but it requires us to have an understanding of what a line integral is. So I'm going to go ahead and just kind of tell you that definition, and then we're going to talk about how it relates to things that you've already done, okay? So our second definition for voltage, and this is the one that we are actually going to kind of use a lot more in this class, is that voltage is simply the difference in electrical potential between 2 points in a circuit. Okay. So all of you guys at some point have used a multimeter to measure a voltage, okay? And when you use that multimeter, you connected one lead to some point in the circuit, and you connected, so let's say that you had the red lead somewhere, and then you connected the black lead somewhere else. What you were doing was literally measuring the difference in electric potential between those 2 points. And the the voltmeter returned the voltage, which is just that difference, okay? So this comes from the line integral because we know from the fundamental theorem of calculus that we could just evaluate our function at points A and B and take the difference, and that would be that voltage A and B because we have a line integral. So it is literally the exact same thing, okay? So anytime that we have measured a voltage ever, we have been exploiting this second relationship. And this is the one that we're going to use fundamentally for this particular class, okay? We're just going to consider that if we have any 2 points in a circuit or network, if we can take the difference in electrical potential, we can have some voltage. It doesn't matter if we have a closed circuit, an open circuit, whatever. If there are 2 different points, we can measure some voltage between them, okay? And what that voltage comes out to be will be dependent on things like Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law, which you learned back in the Engineering 120 series, and we're going to revisit again in this class come Monday, okay? So before I move on from this kind of definition of voltage, does anybody have any questions for me? All right. So let's talk about how we are going to define a voltage, okay? So let me call this part right here defining slash representing voltages in circuits. So I'm going to draw some generic circuit element A here, okay? So here's our generic circuit element A, and I'm going to put some ellipses on top and some ellipses on bottom here. And what these ellipses represent is really that just A is part of some larger circuit or network. And we are going to consider that that network is energized, meaning that the voltages and things that we're going to look for probably aren't going to be zero unless we have explicit reasons, okay? So the most common way that we would define or represent a voltage across this element A is what I'm going to call the American style. So let me just write that down here. And so we'll have some magnitude. So I might represent this symbolically as something like VA, like so. And we might have a number associated with it. So I'm just going to call this, let's say, 5 volts, okay? So what I'm saying by writing that VA is equal to 5 volts is that there is a difference in electric potential of 5 volts between the two terminals across this element A, okay? Now, this is an incomplete definition or representation of the voltage because not only does voltage have a magnitude, but it also needs to have a polarity. Essentially, we need to define which one of those two terminals is higher in electrical potential than the other one. So I'm going to arbitrarily choose this top terminal to be what's called the positive polarity terminal. And then by default, my bottom terminal will be the negative polarity terminal. So what these polarity symbols mean is that the top terminal is 5 volts higher in electrical potential than the bottom terminal. If you look at a Duracell battery or something like that, and you look at the packaging of it, it usually literally has a plus sign on one side and a minus sign on the other to let you know physically which terminal of the battery is at a higher electrical potential than the other one. We're just going to do that for literally everything. Okay. So we could arbitrarily define the polarity of the voltage drop across this element A as positive polarity on bottom and negative polarity on top. I'm going to represent this voltage symbolically as what I'm going to call VA prime. And I would like for you guys to, I guess at this point it would be a guess, but some of you might have some inference here as to what the magnitude of this voltage would be with positive polarity on bottom and negative polarity on top. Anybody have any thoughts?
-5 volts.
-5 volts, exactly right. So swapping the polarities symbols on our element is literally the exact same thing as if we had swapped the leads on our multimeter. I'm sure at some point, at least some of you accidentally measured a negative voltage or something like that back in your Engineering 120 classes, and the way to rectify that was to literally switch where the red and black leads were located. If you switch those guys around, your negative voltage got converted into the exact same positive voltage. And what you were actually doing was swapping the polarity of the voltage that you had assumed originally. Okay. So if you ever are given a circuit or anything like that, and you have a negative voltage, simply swap the polarity and that will give you a positive voltage. All right, so I am not arrogant enough. I'm plenty arrogant, but I'm not arrogant enough to assume that you guys are all going to be able to catch what I'm throwing 100% of the time. And some of you may choose to supplement my lectures with watching YouTube videos or something like that. Okay. So I'm going to now show you what the European style for representing voltages in a circuit looks like, just because an overwhelming amount of content creators, particularly in engineering fields, come from places like India and Nepal, where they use the European style as opposed to the American style that I've already shown you. So for what it's worth, if we had that same element A, and we had that same voltage, VA is equal to 5 volts. In Europe, let me put the ellipses here. Instead of drawing a plus sign to indicate the positive polarity terminal and a minus sign to indicate the negative polarity terminal, they instead use arrows. So it might be something, and I'm just going to switch colors here for just a second, like this. So you've got an arrow where the head of the arrow indicates the positive polarity terminal, and the tail of the arrow indicates the negative polarity terminal. Now, I personally find this style of representing voltages a little bit confusing, mainly because A, it's not how I learned it, and B, when I see arrows, I typically associate them with the direction of current flow, okay? So that's why I prefer the American style with nice plus and minus signs that just let me know what's going on. But lots of YouTube content creators and stuff like that, even textbooks, use this European style, so I just want to make you aware of it. If we had the arrow pointing in the opposite direction, that is the same thing as us inverting the polarity of our voltage. So in this case, we would have some VA prime would be -5 volts. Okay. The last way that we may see voltages represented in circuits, and this is actually how I listed out voltage in our mathematical definition earlier, is what's called a double subscript notation. Okay. So here's my element A, the ellipses indicating that this element is connected to some larger circuit. And in a double subscript notation, I need to label my terminals. So in this case, I might use lowercase a for the top terminal and lowercase b for the bottom terminal. And so I would say that I have some voltage VAB is equal to 5 volts in this case, where the first letter in the subscript is the positive polarity terminal, and the second letter in the subscript is the negative polarity terminal. So if I wanted to invert the polarity of this voltage, I would have VBA. I simply switch the order of the subscripts, and that's the same thing as swapping the polarity. And so VBA in this case would be negative 5 volts. So this is the double subscript notation. Method of representing a voltage on a circuit, okay? We're not going to use it a whole heck of a lot in this class in particular. We're going to use kind of a modified version of it when we get to nodal voltages, but I'll talk about that then. But if you go on into subsequent electrical engineering classes like circuits 2 and so on, when we get to complicated three-phase systems, we use the double subscript notation almost exclusively because we have so many nodes and so many voltages that we're interested in that that's actually the most efficient way to represent what's going on in the circuit. Okay, so before we move on to another topic related to voltage, does anybody have any questions about any of these representations? All righty. So the last thing that I want to talk about with regards to voltages for today is the different types of voltage sources that we might see in the circuits that we're going to analyze in this class. Okay. So let's call this section voltage sources. And I'm going to start with the one that you guys saw the most back in the Engineering 120 classes. And that would be the battery. Okay. So this is the schematic symbol for a battery. And in a battery, the long horizontal line is for the positive polarity terminal, and the shorter horizontal line is for the negative polarity terminal of the battery. So inherently, the polarity is already a known quantity when we're looking at a battery symbol. So you may not see it with a plus and minus sign, but always the long line is positive and the shorter line is negative. Okay. And then we also need some sort of magnitude. So I'm going to represent this magnitude symbolically, and I'm just going to call this VDC. Okay. Because a battery is an example of a DC or time invariant voltage source. Okay. Now, one thing that I want you guys to know, and this will kind of help keep track of what I'm talking about here. Anytime I'm representing something symbolically using capital letters, that means that it is a constant quantity. And anytime I'm using lowercase letters, that means that it can vary with time. Okay. So in this case, I used capital V, capital D, and capital C because this is a DC or constant voltage. Okay. Now, I personally don't particularly like the battery symbol because it looks very similar to the schematic diagram symbol for a capacitor. And so it's not out of the realm of possibilities for somebody to accidentally make a mistake and consider a capacitor a battery or vice versa. So instead, I tend to use a generic DC source circuit representation. And so, excuse me, that would look something like this. So here are my two terminals. I'm going to put a circle here in the middle. And inside of this circle, I'm going to have a plus sign and a minus sign. And I hope, obviously, the plus sign is touching the positive polarity terminal and the minus sign is touching the negative polarity terminal. So once again, the polarity of the voltage is implied by the symbol. Um, I'm going to choose to represent the magnitude once again as just some DC or constant voltage like so. And so this symbol is my generic DC voltage source. And this is what you'll see me use the overwhelming majority of the time. Okay. So very similar, we're going to have a generic AC voltage source. Okay. So the symbol is going to be almost identical. So here's my circle, my plus sign, my minus sign, but I'm going to put a little squiggle inside, and that squiggle is letting me know that that voltage is changing in time. Okay. So this is my symbol for my generic AC voltage source that provides some time varying voltage. And I'm going to choose to represent its magnitude, or really it's going to be a function of time, as lowercase v AC as a function of time, like so. So these three voltage sources are what we're going to call independent sources. Okay. Independent. There we go. Sorry, I had to think so long about how to spell that. So when I say that I have an independent source, what that means is that the amount of voltage that are provided by these sources is independent of what they are connected to. So it doesn't matter if I have that battery connected to a 5 ohm resistor or a 900 millifarad capacitor, it's going to provide the exact same amount of voltage. Same thing for my generic DC source, same thing for my generic AC source. It is agnostic of what it is connected to. So regardless of what it's connected to, if I were to measure the difference in potential energy between those terminals, it would return whatever voltage I'm told, okay? Um, Contrasting that, we're going to have a couple of different dependent sources, and I'm going to introduce those over here to the right, okay? So the symbols for these guys are going to be exactly identical. So this is one of the things that tends to confuse students about them. So I'm going to try to explain it to the best of my ability. So I'm going to start with this guy right here. And I'm going to just go ahead and say that this is going to be a voltage controlled voltage source. Okay. So our dependent sources, we're going to be able to see them at a glance because instead of having a circular symbol, they're going to have a diamond symbol in the middle. So that's always, that diamond is always telling us that this is a dependent or controlled source. This is a voltage source because it has an identified positive polarity terminal and a negative polarity terminal because of the plus and minus sign. And because this is a voltage controlled voltage source, I'm going to represent the magnitude of this source as follows. So I'm going to have some scaling factor K, and it's going to be multiplied by some voltage, which I'm just going to arbitrarily call Vx here. So essentially, Vx is some voltage elsewhere in the circuit. It might be the voltage drop across a resistor or a capacitor or something like that. And then whatever voltage drop occurs across that particular component, this particular source scales that voltage by a factor of K. So this scaling factor K here, because we have voltage as our input signal or our controlling variable Vx, and voltage as our output because it's supplying voltage to our system, this scaling factor is going to have units of volts per volt, or we could call it a dimensionless quantity, okay? I'm being very explicit by telling you guys what the units of these scaling factors are going to be, because they're not always going to be presented to you on your circuit diagrams and things like that. So if you ever aren't sure what the unit should be, you could come back and look at these notes and I'll have it spelled out for you. Okay. So in addition to voltage-controlled voltage sources, we also have current-controlled voltage sources. Okay. So let me just write that out. So the symbol for this current controlled voltage source is going to be literally the exact same thing. So it can be a bit confusing. But in this case, my magnitude is going to be given by some scaling factor, which I'm going to call lowercase r. And then my controlling variable is going to be some current Ix, where this current Ix is just the current through some particular resistor, capacitor, inductor, etc. of interest. Whatever that current is, it's scaled by some factor of R, and this guy outputs that amount of voltage. So our scaling factor of R here is effectively converting current into voltage. So it has to have units of volts per amp, okay? So let me recap some things here just really quickly, okay? So this guy right here, goodness gracious, I'm misspelling it and writing it terribly, is what we're going to call our controlling variable. And similarly, this Ix is the controlling variable. Goodness gracious. For this current source, or excuse me, for this voltage source. And then this guy K and this guy R are going to be our scaling factors. Okay. So the controlling variable is what tells us which type of control we have for our source. And the fact that there is a plus and minus sign indicated on our source tells us that it is a voltage source. So if we have any source that looks like this guy right here, it's definitely a voltage source, but then we have to look at what the controlling variable is to know whether it's a voltage controlled source or a current controlled source, okay? So as I mentioned earlier, these guys are examples of dependent sources. And they are dependent sources because the voltage that is provided by them depends on some external quantity. So how do you guys feel about the different voltage sources that we are going to see in this class? Any questions, comments, or concerns? Alrighty. Thank you, Grayson, for the thumbs up emoji thingy. So that's really all that I wanted to talk about as far as voltages go conceptually today. So now I'd like to move along to current, and as kind of a side thing, we're also going to talk a little bit about charge here. Okay. So I'm going to start with charge. Okay. Um, so I'm not going to write down any kind of word-based definition here because it's actually kind of an abstract thing. But we know that all things are made up of atoms, and atoms themselves are made up of, protons, electrons, and neutrons. Protons are positively charged particles, and electrons are negatively charged particles. Okay. And if we aggregate the total amount of, electrons that exceed the total number of protons, then we would say that that particular element has some negative charge. Or if there are more protons than there are electrons, then that particular thing has some amount of positive charge. Okay. Symbolically, charge is going to be represented by the letter Q. Okay. And it can either be a constant quantity or it can vary with time. Okay. The unit of charge is the coulomb, represented by the letter capital C. Okay. As a brief tangent here, essentially this entire class is all about just understanding what the hell electrons are doing at any given moment in time. So like when electrons are separated, that turns out that's what gives us voltages. When electrons are moving, as it turns out, that tells us when we have currents and all of that kind of stuff. So all of electrical engineering is essentially just figuring out what electrons are doing at any given point in time. Okay. So current is going to be represented by the symbol I. Okay. And I'm going to choose to express I as a time varying quantity here. So mathematically, our current I is going to be defined as the derivative of charge with respect to time. Okay. So in order for us to have a current flowing in our system, that means that the charge or the amount of charge that's passing some given point in our system has to be changing with respect to time. If it were constant, so if we always had exactly 5 coulombs of charge passing a particular point, our current would be 0. But if the rate at which charge passes through changes from 5 coulombs in an hour to 6 coulombs in an hour or something like that, then we're going to see some current flowing through. Okay. So our unit of charge based on our mathematical definition, excuse me, our unit for current here based on our mathematical definition, we're going to say that 1 ampere, symbol capital A, is equal to 1 coulomb of charge divided by 1 second. And from this, we can kind of get a definition for current. And I'm going to call current the time rate of change at which charge passes a given point in a circuit. I think we're all, at least in some way, shape, or form, familiar with the concept of current because it literally does represent essentially electron flow in our system. Okay? So what I'd like for us to do really quickly here is work a quick example just so that we can kind of see how the units and things like that get manipulated. Okay. So let's say that the charge that enters the positive polarity terminal of a particular circuit element is given by the expression Q of T is equal to Im multiplied by time plus QM sine omega t, where I'm going to say that IM is equal to 6.3 milliamps. I'm going to say that QM is equal to 2.1 millicoulombs. And lastly, I'm going to say that omega is equal to 1.3 radians per second. Okay? So what I want to find is the current flowing through this element I at time t is equal to 700 milliseconds. So from our definition above, we know that if we want to calculate our current, we simply need to take the derivative of our charge relationship, okay? So I of t is just dq by dt, or the derivative of Im times t plus, goodness gracious, that is not a q, qm sine of omega t. And for what it's worth, this is really about as hard as the calculus is going to get in this particular class. I'm going to expect you guys to be able to differentiate and integrate simple polynomials, and then sine functions, cosine functions, and exponential functions, and that's about it, okay? So nothing too wild or crazy in this particular class from a mathematical perspective. All right, so I'd like you guys as assistants for what it's worth in taking the derivative of this particular relationship. So what's the derivative of Im multiplied by t with respect to time?
So it would be IM plus W or omega. Is it W or omega?
So that's an omega. So
Okay.
you did the first part right. The derivative of that first part right
Right.
here is literally just the Im. Now you're going ahead and doing the second part here, which is great. So you're 100% correct that you're going to pull out an omega.
So you're gonna do omega QM and then cosine omega T.
Okay, omega t. And the derivative of sine is positive cosine or negative cosine. I genuinely don't remember.
I believe it's positive.
Okay. Yeah, I think derivative of sine is positive cosine, derivative of cosine is negative sine, if I'm
Right.
remembering correctly. Yeah, okay. Thank you for that. And so now we could literally just plug things in. So let's do just that, okay? So we're going to have 6.3 milliamps. We're going to have 1.3 radians per second. So radians is a dimensionless quantity, so I'm going to choose to just throw away radians here, and I'm going to represent omega as 1.3 per second, or seconds to the negative 1 power. Then I'm going to have QM, which is going to look like 2.1 millicoulombs. And then lastly, I'm going to have cosine of 1.3 per second multiplied by 700 milliseconds. And since omega is measured in per seconds, I'm going to choose to represent 700 milliseconds in seconds so that the argument of my cosine function is just, actually, let me write out specifically here in this case radians per second so that we know what setting to use on our calculator. So radians per second multiplied by 0.7 seconds. Okay. So if I put this into my calculator, I've got, let's just do this down here a little bit. 6.3 milliamps. Then I have 1.3 times 2.1. So that's 2.73. And that looks like millicoulombs per second. And that is being multiplied by the cosine of that bit. So I'm going to throw that into my calculator. So when I do cosine of 1.3 times 0.7, I get 0.6137. So I'm going to call that 0.614. Okay. So this is kind of a trick question, but if anybody's following along in their calculator, how many of you are willing to admit that when you did cosine of 1.3 times 0.7, you got a different number than I did?
Yeah,
So,
0.999.
yeah. So Joseph got 0.999. Joseph, may I ask you a question? Is your calculator set in radian mode or degree mode?
Well, it's in radians now, but it was in degrees.
Yeah. So that's something that you really need to watch out for. In this class, we are going to be dealing with sinusoidally oscillating signals very regularly. And the frequency at which those signals oscillate is usually expressed by a symbol omega, which is measured in radians per second. So the radian mode of your calculator is going to do a lot of heavy lifting in this class. I try to be very explicit by telling you omega is measured in radians per second to give you guys a very strong hint that you need to be setting your calculator in radian mode, but it is a very easy thing to miss. So I just wanted to point that out to you guys there. So if I keep on following through with things here, first, what's a millicoulomb per second going to be? Anybody have any thoughts?
Should be a milliamp.
Exactly right. So if a amp or ampere is a coulomb per second, then a millicoulomb per second should be a milliampere. Exactly right. Okay. So that's going to look like 6.3 milliamps plus 2.73 milliamps multiplied by that factor of 0.614. And when I put all of that into my calculator, let's see, 6.3 plus what I have stored as X times what I have stored as Y, I wound up getting 7.9755. So let me just call that 976 milliamps. Okay. So I can't emphasize this enough. Units are very important. You're going to see lots of different units in this class. So I highly encourage you guys, when you're working problems out, to pay attention to units and include them in all of the steps. There are some times where you can just kind of tack them on at the end and things will work out for you. There are other times where that methodology is going to bite you in the ass. So I'm just trying to give you fair warning. All right, any question about that particular example problem? So before we move on from here and get into, how we're going to represent currents and things like that in circuit diagrams, I do want to introduce you guys to a secondary unit. It's actually a unit of charge, not current, but this is something that you might see in industry, or you might see actually in your everyday lives, if you're buying like a rechargeable battery for a project or something like that. Okay. So let me just make a note here. Charge is also commonly expressed in what are called amp hours. Okay. So amp hour is an industrial used unit of charge. And the reason why it's used, particularly with batteries and things like that, is because it gives you an indication of not only the capacity of charge that your battery can hold, but also it gives you an indication on how long it's going to take to fully charge your battery given a particular current. So what I mean by that specifically is that if you have a battery that's, let's say, 2000 milliamp hours, okay, so let me just write this out real quick, okay? So Q is 2000 milliamp hours, okay? If you're trying to charge this battery using a USB standard that can only charge at, let's say, I is equal to a maximum of 2 amps, how long would it take you to fully charge this battery? Well, 2 amps is the same thing as 2 milliamps, so it seems like it'll only take us an hour to charge the battery. So that's why that particular unit is so convenient for batteries and things like that, because if we know what our charging current is, because there are standards, then it tells us how long it's going to take us to fully charge a battery. So anyway, I just wanted to make you aware of that particular unit of charge because you may see it in your everyday life. Okay, let's talk about representing currents. So go back to my tried and true generic circuit element A. So let's say that I have 3 amps of current flowing through this element A. I could represent that symbolically as, let's say, something like this, IA. Okay. Now, once again, if I only know the magnitude of the current that's flowing through my element, I have kind of underspecified this quantity, okay? So when we were dealing with voltages, we learned that voltages had both a magnitude and a polarity. When we're dealing with currents, they have both a magnitude and a direction. So I'm going to say arbitrarily that there are 3 amps of current flowing down from the top terminal through element A and out the bottom terminal. And so if I defined some current, let's call it IA prime as flowing up, what would the magnitude of that current be?
-3 amps.
-3 amps, exactly right. So essentially, if we flip the direction of our arrow, that's the same thing as just multiplying by a factor of, or multiplying our magnitude by a factor of -1. So anytime you wind up having some negative current, if you want to get rid of that negative sign, just change the arrow that the current is pointing or is flowing in. Okay. Um, as far as I am aware, there's pretty much this only one way to represent how current flows on a circuit diagram. So we don't have to deal about, a European method or anything like that here. This is pretty much just it. Okay. Anybody have any questions on anything that we've talked about with regards to current thus far? All righty. Oh, Trevor, it looked like you unmuted yourself. Did you have something to ask or say?
No, sir. I was saying no, sir.
Okay. Thank you. Okay, so the last thing that we're going to talk about with regards to current is then what type of current sources that we're going to see in the circuits that we deal with in this class. Okay. Running out of room, but I think I can squeeze them in down here. So I'm going to start, and maybe I'll put the labels out to the side or something like that. So this is going to be my generic DC current source. One question that I get asked fairly regularly, and this is, sorry, I accidentally made that D look too much like a B for my taste, is, what are current sources and where do we see them? And the short answer is that most of us probably don't see actual current sources in our everyday lives, okay? You can buy current sources as specialized pieces of laboratory equipment. But more likely than not, in classes like this DC current source is actually representing a transistor amplifier circuit that is capable of driving some fixed amount of current around a circuit. Now, this class has literally nothing to do with transistors whatsoever. So this symbol is just a way for us to kind of scale that down to something that's more manageable without having to know about how transistors and things like that behave. Okay. So you can go to a grocery store and buy a voltage source in the form of a battery, even gas stations and stuff like that. You cannot do that with current sources. They are rather expensive pieces of equipment. But from an analysis perspective, we are going to see them fairly regularly. In real life, not so much. Okay. So we also are going to have our generic AC current sources. So same exact symbol, except there's a squiggle in the middle of it, letting us know that our current is varying in time. I'm going to draw our magnitude as IAC as a function of time. And these are the two different independent current sources that we'll see. And then much like with the voltage sources, we're also going to have two dependent current sources. So let me do the first one here. So just like with the voltage sources, we're going to use a diamond symbol. But instead of having a plus and minus sign, instead we're going to have an arrow. And this first one is going to be a current controlled current source. So its magnitude is going to be represented by K, some scaling factor, times Ix, our controlling variable. And the units for this scaling factor K are going to be in amps per amps, or once again, a dimensionless quantity. So that's how I'm getting away with using the same symbol for a voltage-controlled voltage source and a current-controlled current source. K in both cases really just doesn't have units, okay? In addition to current-controlled current sources, we can also have voltage-controlled current sources. So that's going to have the exact same symbol. But in this case, I'm going to call the scaling factor lowercase g, and my controlling variable is going to be some voltage. In this case, I'm going to call it Vx. So this scaling factor g is converting an input voltage into an output current. So that means that G needs to have units of amps per volt, okay, in order for the units to work out right on this particular source. So once again, these guys that I'm underlining here in blue are my controlling variables for these sources. And these guys that I'm underlining here in orange are my scaling factors for these sources. Okay. I know nobody has asked any questions or anything like that yet. We haven't really seen a dependent source used, so it's okay that you, I guess, don't realize you're confused about them yet. But when we start seeing them more often, if things aren't making sense, please, please, please ask, and I'll be happy to explain things. Okay, anybody have any questions with regards to current sources?
For the name of our second dependent source, controlled voltage source, should it be a current source?
It should, Colin, thank you for that. I just wrote it down incorrectly.
Yes, sir.
It is very much a current source because it has an arrow inside of the diamond, not a plus and minus sign. But thank you very much for that catch. Any other questions or concerns? All right, so now let's move on to power and energy. Okay. So power and energy are very related to each other. And when we get to our word-based definitions for them here in a moment, it's going to kind of seem like we have a circular argument because our definition for power is going to be dependent on energy, and our definition for energy is going to be dependent on power. So I'll try to explain the difference in things here really quickly, okay? So power, mathematically, we are going to define it in an electrical system as simply the product of voltage and current, okay? So that means we're going to have some time varying voltage V of t multiplied by some time varying current I of t. If we look at this dimensionally, we have volts, which we know is a joule per coulomb, multiplied by amps, which we know is a coulomb per second. And we see that those coulombs cancel each other out, and we're left with a joule per second, which is more commonly known as a watt, symbol uppercase W, okay? And so from this definition of the units for power, we can actually kind of see that power is just the rate at which energy is transferred, because joules are the units of energy and seconds are the units of time. So it's just energy per time, okay? We'll write that down in a moment. Energy, W, is going to be defined in this class as simply the integral from one point in time we're interested in to some second point in time we're interested in of power with respect to time, where the units of energy are a fundamental unit. So we're going to have just the joule, symbol J, okay? So from our word-based definitions, we're going to say that power is the rate of change of energy transfer in a system. And we're going to say that energy is the total amount of power absorbed or supplied over a fixed interval of time. Okay. So these two guys are inherently linked to each other. So if entergy is the integral of power, we could just as easily say that power is the derivative of entergy. Or excuse me, I said entergy instead of energy, but you guys catch what I'm throwing there, hopefully. Okay. Just for what it's worth, there is another unit of energy that you guys may see in your day-to-day lives. Okay. So I'll just write that out here. So another common unit for energy, particularly in electrical distribution systems, is the watt hour, or more commonly actually would be the kilowatt hour. So I don't know how many of you guys actually pay attention to your electricity utility bill, but the amount of energy that you use in any given month is expressed as a number in kilowatt hours. Okay. So that's the unit of energy used by electrical utilities to tell their consumers how much energy they're using. It's actually funny because most people probably call it a power bill, but it's actually telling you the energy that you consumed, not the power. So anyway, anybody have any questions about our word definition or mathematical definitions for power and energy? Okay, so I am about to introduce a concept here. And it is something that over my, I guess it's now 8 years of teaching this class, I have seen countless numbers of students struggle with, okay? So I'm going to try to explain it as succinctly and simply as possible, okay? So what we're going to talk about here, and it is related to power and energy specifically, is what's called the passive sign convention. And this is the convention that we are going to use for all of the circuits that we're going to look at in this class, okay? So let's say that I have some generic circuit element A, like so. Okay. And this generic circuit element A is part of some larger electrical system represented by those ellipses. Okay. I'm going to define the voltage drop across element A as positive polarity on top, negative polarity on bottom, and I'm going to describe its magnitude as just VA. Okay. Now, I don't have any knowledge or any care as to whether or not that magnitude VA is a positive quantity or a negative quantity. It is irrelevant to what we're about to discuss, okay? I'm also going to define the current that's flowing through element A. And in this case, I'm going to define that current as follows. So here's IA, and we can see that IA is flowing into the positive polarity terminal of element A, and transversely, that means it must flow out of the negative polarity terminal of element A as well. So in this particular case, where current is flowing into the positive polarity terminal, we can say that our absorbed power is simply the product of VA and IA, okay? So this is the power absorbed by our element, and then the power supplied by our element is just going to be negative VA times IA. So this tells us that absorbed power is just the negative of supplied power and vice versa. So if an element is absorbing negative power, that means it's supplying positive power. Okay. So let's contrast this with circuit element B over here to the right. Once again, this circuit element is going to be part of some larger network circuit or system. I'm going to define the positive polarity terminal for voltage VB on top, but now I'm going to define our current IB as flowing into the negative polarity terminal, or transversely, we can think of it as flowing out of the positive polarity terminal. And in this particular case, our absorbed power is going to be negative VB times IB. And our supplied power, goodness, is going to be positive VB times IB, okay? Now, I've tried to explain this as in an easy to understand package as I can, but if you're still not quite catching this, which is fine, you can always ask questions. But really, let's think about it from the context of what we learned about, currents and directions and all that kind of stuff a little while ago, right? So in our first case on the left, we have the current that is flowing from left to right and then down through our element. In the second case, we have a current that's flowing from left to right and then up through our element. So we have those two currents and they're flowing in opposite directions. So it should make sense to us, hopefully, that our powers get opposite signs in each of those cases, right? Because the current's going the other direction and power is just the product of voltage and current. So if currents are going in different directions, we know that they should have different signs. And then multiplying them by the exact same polarity voltage means that we're going to yield powers that have different signs as well. Okay. So to, wrap this up very succinctly, essentially, if we ever see current flowing into the positive polarity terminal of an element, I times V gives us absorbed power. Whenever we have current flowing into the negative polarity terminal of an element, I times V gives us supplied power, okay? So that is the passive sign convention in a nutshell. Okay? So if you're ever working a problem and you get the right magnitude but the wrong sign, chances are you weren't considering the passive sign convention correctly, or you weren't paying attention to whether you were asked for absorbed power or supplied power. I will tell you, and those of you that are repeating the class can verify this if you want to, I am absolutely enough of an asshole that on your exams and things like that, I will have both the correct answer and an incorrect answer, meaning that we'll have the exact same magnitude but the wrong sign. And I am expecting you to be able to know which of those two answers is correct. I try to set things up such that you receive partial credit if you get the right magnitude but the wrong sign, but you'll only get full credit if you have both the right magnitude and the right sign on your power calculations. And you're going to see this on practically every single homework assignment, every single in-class assignment, and every single exam over and over and over again. So if you have any questions about this passive sign convention, please don't hesitate to ask now or later on when it trips you up or anything like that. I will go over it with you as many times as we need to until you feel comfortable with the rules. All right, any questions regarding the passive sign convention? Okay, so I would like to work an example with you guys, and this is fairly simple and straightforward, but it will help us reinforce some of this passive sign convention stuff. Okay. So let's say that we have the following circuit. Here's some element A. Here's some element B. Here's an element C. Here's an element D. Here's E. And lastly, over here to the right, we've got F. Okay. So let's say that this is the voltage VA, and this is the direction for the current IA. This is VB. And this is IB. This is VC and IC. This is VD and ID. This will be VE and IE. And then this will be VF and IF. And out here to the right-hand side, I'm going to give you numerical values for all of those quantities, okay? So let's say that VA is negative 8 volts. VB is negative 2 volts. VC is positive 10 volts. VD is also positive 10 volts. VE is negative 6 volts. And VF is negative 4 volts. Over here to the right, I'm going to put down our currents. So we're going to say that IA is 7 amps. IB is negative 7 amps. IC is 15 amps. ID is 5 amps. IE is 3 amps. And IF is also 3 amps. And I want us to determine the power absorbed by all of these circuit elements. So let me write that down. So I'm going to start us off here. So we're going to start with element A. And I know that the voltage drop across element A is -8 volts. So I'm going to put -8 volts. And I know that the current flowing through element A is 7 amps. So I'm going to put 7 amps over here. And so really what I'm doing now is I'm simply deciding whether or not I need to put a negative sign out in front, okay? And so how I make that decision is whether or not the current is flowing into the positive polarity terminal or into the negative polarity terminal. So since I am trying to determine the power absorbed by each of these elements, anytime the current is flowing into the positive polarity terminal, I leave it alone. And anytime the current is flowing into the negative polarity terminal, I need to add a negative sign. So what I'd like for somebody to answer is the current IA flowing into the positive polarity terminal or into the negative polarity terminal of element A?
Positive.
It is flowing into the positive polarity terminal, which means we don't need to do anything. So element A is absorbing negative 56 watts of power, okay? So over here to the right, I'll do PB, same situation. I know that my voltage is -2 volts. My current is -7 amps. In this case, is my current flowing into the negative terminal or into the positive terminal of element B?
Negative.
So since the current is flowing into the negative terminal and I'm trying to find absorbed power, what do I need to do?
Put a negative in front.
Exactly right. Thank you very much, Joseph. So negative times -2 times -7 is just going to look like -14 watts. And we can keep on doing this with the other elements, and I'll just do them quickly, right? So here's element C. So we have 10 volts times 15 amps. The current IC is flowing into the positive polarity terminal, so I leave it alone. So this guy looks like 150 watts. When I get to element D, I have 10 volts times 5 amps. The current is flowing into the negative polarity terminal, so I need to put a negative sign, so that looks like -50 watts. When I get to element E, I have -6 volts times 3 amps. The current is flowing into the positive polarity terminal, so I leave it alone. So that comes out to be -18 watts. Lastly, for element F, I have -4 volts times +3 amps. Once again, the current is flowing into the positive polarity terminal, so I leave it alone, and I get -12 watts. So the last thing that I would like for you to do really quickly before I let you get to your ICA or the rest of your afternoon if you so choose, is I would appreciate if somebody added all of those powers together and told me what result they got.
0.
0.
Okay. So that brings me to my last very brief topic here, and that's what's called Telegen's theorem. Okay. So Telegen's theorem is related to power as well. So this is still kind of under the blanket of power and energy. So Telegen's theorem states that the total amount of absorbed power in a system must, I can fix that, equal the total amount of supplied power in a system. So in this case, since we counted everything as absorbed, it has to equal 0 because there are no supplied power. But we could have just as easily tried to figure out, how much was supplied in the system, and we would have gotten the exact same results, except everything would have been flipped by a minus sign. Or we could have gone through and said, hey, how much absorbed power by elements A, C, and D, how much supplied power by B, E, and F, and we would have found out that they would have resulted in the exact same amounts as well. So essentially, Telegen's theorem is really just kind of a dumbed down version of the law of conservation of energy that says that energy can't be created or destroyed, so the total amount of it must be conserved. Okay. All right, so that's the last thing that I wanted to talk with you guys about today. So you're free to work on your in-class assignment if you choose to do so. I'll hang out on Zoom for the next 20 minutes or so if anybody has any questions. If you choose to dip and enjoy your weekend a little bit early, I completely understand, and I hope that you have a happy and safe weekend. Talk to you guys later, etc.